Hello students, welcome to Linear Algebra. This is the first lesson video of this course, so let's begin with the preliminaries. First, the absolute basic. The property of real numbers. We have some algebraic properties like these. And inequality properties like these. Alright, all good. And third, the completeness property. The set of real numbers completely fills up the number line. Now the first two properties are not really worthy of our class time in 3000 level course. Let's talk about the third property briefly. What do you mean by this? Let's go back to the first property of inequality property, the trichotomy here. What does it mean? Given pair of real numbers a and b, one and only one of these three holds. A is less than b, a is greater than b, or a and b are equal. So what does it tell us? This tells us that every real number corresponds to a point in a line. Bigger number to the right, smaller number to the left. Even bigger number, push it further to the right. Even smaller number, push it further to the left, and so on and so forth. Now, does it completely fill up the line? The answer is yes, and that requires another property or another axiom. So for example, set of rational numbers also satisfy this trichotomy. So set of rational numbers can be placed on a line. Set of integers also can be placed on a line. But then again, they do not completely fill up the number line. Real numbers do. And the implication, well, all kind of geometrical objects correspond to real numbers and real number arithmetic. So we can use real number arithmetic in algebra to answer questions about geometry. And that opens up entire field of analytic geometry and coordinate systems and so on and so forth. Okay, so much about the property of real numbers, and let's talk just a little bit about elementary applications. How do I define subtraction and division? By adding additive inverse or multiplying multiplicative inverse. Properties of 0. All good? All right. Properties of 1. Okay. And properties of signs, pluses and minuses. I guess all good. All right. We are done with the section 1 of this notebook. Let's go to section 2. These are from pre-calculus. Previously, section 1 came from college algebra. Okay, let's begin with vector quantity, and let's stick to 2D for simplicity and easier viewing. Vectors have three properties. It must have magnitude, it must have direction, and it must follow algebraic rules. Here's a visualization of magnitude. Blue and red share the same magnitude. Please note that these two arrows have the same length, and we can represent like this, using absolute values. Two different vectors, yeah, but magnitude is the same for both. Here's a visualization of direction and a notation. Two different vectors, but same direction, and we use this notation, the hat notation, to represent the direction. It's the same direction. And finally, algebraic rules. Well, there are two algebraic operations. One is addition. Blue plus red is purple in this case. And please visualize this one as kind of a large object standing on here in the starting point. And a group of people are pulling it in this blue direction and also in red direction. What happens in the end? This large object will be pulled toward the purple direction with this kind of new magnitude. That's the idea. And the best, of course, will be very small angle, or ideally angle is 0, so blue and red in the same direction, in that case, the most effective. And the opposite case, they're pointing the opposite direction, 180 degrees. In that case, we have just tug of war, and then the objects down here will not move at all or move very little because purple will become pretty close to 0. That's vector addition. Next, scalar multiplication. It is just multiplying a real number, which we call scalar. In this particular case, we are multiplying blue vector by 1.53 something, about 1.5. So this purple vector is pointing toward the same direction, but about 54% longer. So, okay, it's a little bit longer than 1.5. Let's run it again. And this time even longer, 1.7 something is multiplied. And this time, heck of a lot shorter because we are multiplying only 23.7% or something. Oh, come on. I want negative number. Okay, we got it. Negative 0.28, excuse me. That means this purple is opposite direction and it's about 28.17% of the original. And that's what scalar multiplication is. So there are two types of operation, vector addition and scalar multiplication. With all these algebraic rules, we have so-called a vector quantity. An interesting thing is we have to have these three, magnitude, direction, and algebraic rules. But the starting point is not one of those characteristics. As you can see in this picture, blue, red, green, and brown, we have 4 vectors, but they're all the same. They all start in different places, but that doesn't matter. Magnitude and direction are the same, so these are all same vectors. As a matter of fact, these represent so-called free vectors. They are so-called free vectors and tangent vectors. Tangent vectors depend upon the starting point, and those are the kind of vectors you deal with in physics class. Free vectors, on the other hand, are completely free. It does not depend upon the starting point. In undergraduate math level, we consider only free vectors. Tangent vectors are usually covered in physics class to a certain degree, but the mathematics of tangent vector can be a little bit hard, and it may be possible to consider this in undergraduate level, but I don't know. I'd rather cover it in graduate level differential geometry class. So in other words, in this class or in any undergraduate class, we're going to be considering only free vectors. Alright, so much for vector quantities and visualization. And let's talk about some other aspects of vectors. Let's begin with the components. Remember, all the vectors we deal with are free vectors, so you can just move it around and then make it starting from the origin. Then what happens? The endpoint corresponds to a certain point x comma y, and that precisely gives you how much to the right and how much up you have to move. And that's the components notation of the vector. Now, this notebook was originally written for pre-calculus and calculus and multivariable calculus, partly trigonometry. So I'm using Stewart's and Sullivan's textbooks notation using triangular bracket. But in 3000 level, we do not use triangular brackets for vectors. We use parentheses. Why? Well, here are some rationales. Number one, at this level, at 3000 level, students will not get too confused with two different notations, one for point and one for vectors. Second reason, even more important, as a matter of fact, there is no distinction between points and vectors. Everything is free vectors, so you can move any vector starting from the origin, and then there's one-one correspondence between the vector and the endpoint. So there's no distinction between one and the other. As a matter of fact, that concept is a little bit more elaborated here in the next subsection. Subsection, excuse me. It's called position vector. Move it along and then make it start from the origin, called position vector. And you can see there is one-to-one correspondence between the point, the ending point, and the vector itself. So there's no reason to distinguish one and the other. So we can use the same notation, parenthesis notation, in place of the triangular bracket notation. Triangular bracket notation, I will never use it after first week, okay? Because it's reserved for something else. So after first week, all the vector notation will be done in parenthesis notation. Okay, all right. Next, displacement factor. It's not a position vector. It starts from the arbitrary point, and then it measures how much it moved, how much displacement, how much the point was displaced, literally. x2 minus x1 to the right, y2 minus y1 upward. In this case, 4 units to the right, negative 2 units up. Displacement is not that important for this course, so let's just move on. Magnitude. How do you calculate magnitude? Here's a visualization. We just use Pythagorean. If we have displacement factor, again, Pythagorean. Simple deal. Now that we talked about magnitude, we are now ready to talk about unit vectors in a certain direction, and we can define it like this. Unit vector means a vector whose magnitude or length is 1, and a unit vector in the direction of v, we define it like this. If we define like this, what do we have? Let's see, what if I take absolute value or the magnitude of this? That means the magnitude of this. And then what do we have? We have cancellation. Numerator and denominator are the same, so we have to have 1. So if we define a vector like this, always it has magnitude 1. And the direction is same as this original vector v. So what we end up with is a unit vector, or the vector with magnitude 1, but the same direction as the original. Because there are infinitely many directions, there are infinitely many unit vectors. Among those, 2 or 3 of them are extremely important. In 2 dimension, these 2 are important. Horizontal and vertical. Visualization is here. Horizontal is blue and vertical is red, I and J respectively. And then if you're in 3D, then you need one more, I, J, K, in XYZ direction. In n-dimensional case, of course, you're going to run out of alphabets, so you cannot use I, J, K, L, M, things like that. You need E1, E2, E3, and so on. And this is what we are going to do, and I just adopted our textbook's notation. So we are not going to use this bracket notation, triangular bracket notation anymore, because our textbook author uses parentheses. Okay, let's go back to this example again. W is this vector, 3, 2, 3 units to the right, 2 units up. And that's equivalent to multiply 3 to this blue, which means triple the length. So this vector come all the way up to here, to the end of this triangle. And then this red vector is doubled all the way up here. So if I add them up, then we have diagonal using the parallelogram law. This is rectangle, but it's parallelogram nonetheless. So we talked about standard unit vectors. All right. The final topic, vector addition and scalar multiplication. All right. Scalar multiplication is slightly easier, so let's talk about it first. Multiplying by scalar k means multiplying scalar k to all direction. Here's a visualization. Okay, here we go. Blue is the original, and I multiplied by 0.67. So what happens? In x direction, we have this same reduction, 67% of the original. And then y direction, again, 67.4% of the original. If we had z direction, and then if we had higher dimension, multiplying k to each component. It's easy to see. Just rescaling. Now, a little bit harder one is vector addition. Well, in terms of computation or in terms of formula, it's easy. As a matter of fact, you can simply add up each component. Why is the question, and let's answer that. Okay, here's a visualization of vector addition, blue plus red, using the parallelogram law. All right. Next, here comes the visual proof. Please remember, V1 is blue, V2 is red. Look at this picture. Blue triangle corresponds to V1, red triangle corresponds to V2. Now, in order to go from origin all the way to the end, to the right, I have to move x1 following blue triangle and x2 following the red triangle. Do you see that? From here all the way over there is equivalent to x1 plus x2. How about vertical? Same deal. x1 vertically plus y1 plus y2. This picture says it all. And that's how we can summarize and justify the computational formula. We can simply add up each component, x component, y components. If we have 3D vectors, then z components. Just add them all up, and that's the vector addition. So in summary, what did he do? We talked about vector quantity, and we have magnitude, direction, and algebraic rules. And then we talked about components. So we talked about vectors in coordinate plane, and that generated vector addition and scalar multiplication using coordinates. So add up the x coordinate, add up the y coordinate, that's 1, and multiplying k to each component, that's 2. And then combine those with standard unit vectors. You can represent any component into the sum of vectors xi plus yj like this. Example, purple vector 3, 2 is equivalent to 3i plus 2j, this expression. If we have n-dimensional case, then we're going to run out of characters. So instead of I1, I2, and so on, we use, instead of ijk, we use E1, E2, and so on. And that's the only thing. Let's see, do we have some example here? Okay, just a couple of minutes. Okay, all right. Expressed 2a plus minus 3b in components in terms of I and j. Okay, in component, represent everything to component. Instead of I plus 2j, express those in components, 1, 2, and then apply vector addition here. 2a minus 3b, okay, 2a minus 3b. This is a, and that's b, isn't it? And then multiply by 2, multiply by -3, which means multiply each component. That's a scalar multiplication. And then add them up. Just add up the x coordinate, add up the y coordinate, and that's it. What if you use ij notation? Same thing? Yes, same thing. Express b as not 4, -3, but 4i minus 3j. And then we use the typical algebraic rules, distributive law, associative law, and so on, just like using any character. And then we end up with same expression in the end, -10i plus 13j, -10, 13. The other problems using other formulas, magnitude, unit vector, I can leave all those to students.